we are going to discuss isomorphism closure subcategories, and then we'll also discuss the skeletons of categories. So we start this lecture with the definition of isomorphism closed and isomorphism dense subcategories. So the definition goes like this. So suppose we have a full subcategory of a category B, say A. So a full subcategory, say A of a category B. So this is called uh, so the first item is isomorphism closure. So a full subcategory A of a category B is called isomorphism closure. Uh, Provided that every object in B is isomorphic to some object. I mean, uh, provided that every B object. So if we consider an object B in the category B, so any B object that is isomorphic to some A object, say to some A object, so is itself an A object. So if the category A, if the full subcategory A of category B is such that every B object that is isomorphic to some A object is itself an A object, and we call this full subcategory A to be isomorphism dense. So we call this A to be isomorphism dense if every B object is isomorphic to some A object. Provided that every B object, I mean some object in B is isomorphic to some A object. So in that case we call the category A of B the isomorphism dense subcategory of B. Now we have a short lemma here. So the lemma states that let A be a full subcategory of a category B. Then the following are equivalent. The first item is A is isomorphism dense subcategory. A is isomorphism dense subcategory of B. The second item is the inclusion functor Let us take I from the category A to the category B is isomorphism dense. And third is that uh, the inclusion functor I from category A to category B is an equivalence. Note that an equivalence is a functor which is full, faithful, and isomorphism dense. So a functor having these three properties is said to be an equivalence. And in that case, the categories are said to be equivalent. So let us prove this. So we are given that the A is a full subcategory of category B. So that means the inclusion functor is an embedding as well as a full functor. So let A be a full subcategory of B. So this means the inclusion functor, then the inclusion functor I from category A to category B uh, is an embedding and full. So it is both full as well as an embedding. The reason for this fullness of this functor is that the category is the full subcategory. So since A is a full subcategory of B, now let us assume that the first item is true. I mean, we are going to assume A is an isomorphism. A is isomorphism dense subcategory of B. So this is first implies second. So suppose A is an isomorphism dense subcategory of B. We have to show that the inclusion functor is also isomorphism dense. Now, by definition of an isomorphism dense subcategory of B means that every B object is isomorphic to some A object. In that case, the category is said to be isomorphism dense. So, so A being the isomorphism dense subcategory of B, that means every object in B is isomorphic to some object in A. So therefore, every object in A is isomorphic to some object in B. So let us consider some object B in the category B. So let us take the object B in the category B. Now to show I is an isomorphism dense subcategory, we have to show for this object B in category B, there is some object A in the category A, which is whose image under I is isomorphic to B. So a B is an object in A, then there exists an object, say A in the category A, such that A is isomorphic to B. This follows from the hypothesis that A is isomorphism, then a subcategory of B. So, but if we look at the object A, it is same as the image of object A under this inclusion function. Now, this IA turns out to be an object inside B. So, this would imply, so thus I of A is isomorphic to B. Now, what we proved here, we chose an object B inside B, and we proved that there is some object A in A such that I of A is isomorphic to B. So this would imply I is isomorphism dense. So hence I is an isomorphism dense function. Now we have to prove second implies third. So we are going to assume second is true. So suppose the inclusion functor I, which is from the category A to category B. So we are going to assume this is isomorphism dense. Now, what we have to prove? We have to prove the third item, which says that this inclusion functor is an equivalence. Now, in order to prove this I is an equivalence, it suffices to prove I is full, it is faithful, and it is isomorphism dense. Now, the fullness of I and the isomorphism denseness of I is given, and the faithfulness of the functor I follows from the fact that I is embedding. So this is trivial. So then I is clearly an equivalence, since uh, I is full, faithful, and isomorphism dense. Finally, we have to prove third implies first. So we are going to assume I is an equivalence. So suppose the functor I from the category A to the category B is an equivalence. Now, that being true would imply that I is full, faithful, and isomorphism dense. So then this I is full, faithful, and isomorphism dense. We have to prove that A is isomorphism then a subcategory of B. So in order to prove that, let us pick some object in B. So let B belongs to the B be any object. So we have to prove there is some A object which is isomorphic to B. But this I being the equivalence means this I is also isomorphism dense. So this would imply, so hence there is an object, say A in A, such that the image of A under I is isomorphic to A, sorry, to B. But I of A same is same as A, so that is A is isomorphic to B. Therefore, every B object is isomorphic to some A object. So this proves the lemma. So, so if we drop any hypothesis in the uh, argument of this lemma, this would not be true. Um, for example, if we consider the category, so this is the example. So if we consider the category, say set, so consider the category, say set, then if we uh, so if we consider the category set of all sets, then the category, say A. So if we look at the category, I mean the subcategory, then the subcategory A, which consists in the single object. So with single object, say n, which is a set of natural numbers. This is a set of natural numbers. So this is actually a full subcategory of the categories set. But this category is neither isomorphism closure nor isomorphism dense. Now, why this subcategory is not isomorphism closed? Because if we look at the category A, so the object class in the category A is uh, just the singleton, I mean the set of natural numbers. Now, if we look at the category set, here we have the object class, I mean we have Z, an object in the category set. Now this object Z, this is isomorphic to N, so they are actually isomorphic, but this Z is not an A object, because the object class of A is just the singleton N. So this is the reason this category is not isomorphism closed. This is also not isomorphism dense, because we have an object, say R here. So this R is an object in the category set, but this R is not isomorphic to any A object, because here we have the countably infinite set and this is the uncountable set, so they are not isomorphic. So this is the full subcategory, which is neither isomorphism closed nor isomorphism dense. So all full subcategories need not be isomorphism closed or isomorphism dense. So however, so this is the full subcategory of the category set, because if we look at the home set of A, which is actually the set of morphisms from n to n, this is same as, so these are the, this is the morphism set in the category A. This is same as the set of morphism set from the object n to n in the category set. So they are equal. I mean, this the equality which shows up here implies that this A is a full subcategory of set. However, this category is neither isomorphism closed, so this is neither isomorphism closed nor isomorphism dense uh, in A. In S, sorry, in category set. However, if we look at in the full subcategory of all, I mean, countably infinite set, then this category A and the category of all countably infinite sets are, I mean, these two categories are uh, so if we, so however, A is equivalent to, so this is equivalent to uh, the isomorphism closed full subcategory of the category set consisting of all countably countable infinite sets. So if we look at the collection of all, I mean, if we pick up all the elements, I mean all the objects in this category, uh, having, I mean all those sets which are countably infinite, then that subcategory, so this is the all countably infinite sets. So this is the category of all countably infinite sets. So this is actually a full sub category of category. This is a full subcategory of the category S set, and at the same time this subcategory is equivalent to the category A, which contains just the single object. So this these two categories are equivalent. I mean, there is a function from category A into this category, say F, which is full and faithful as well as isomorphism dense. Now we are going to move to define skeletons. So this is the definition of a skeleton. So a skeleton of a category is actually a subcategory of the category of the given category. So a skeleton of a category is a full subcategory. Mm, so it's a full subcategory in which no two distinct objects are isomorphic. So if we are given a category A, then a subcategory B, which is a full subcategory. So we forgot to mention here this subcategory also is isomorphism dense. So this is full and isomorphism dense subcategory. So if we are given a category A, then a category B is said to be the skeleton of A if B is a full isomorphism dense subcategory of A, such that if we pick two distinct objects in the category B, those two distinct objects uh, are non-isomorphic. So this is the definition of this skeleton. So one so these are the examples. So if we consider the category set, so let us consider the category set. So this is a category of all sets denoted by set. So then the full subcategory of all cardinal numbers is a skeleton for set. So then the full subcategory uh, of all cardinal numbers is a skeleton for the category set. So one should note here that this skeleton need not be unique. However, they are unique up to isomorphism. So what this mean here? So we have the category set here, and in this category we have all the objects here of all are of all um, cardinal numbers of all. So given any, so if we have, say, lambda is any cardinal number, so this is, then we have an object here. So in the subcategory we have the object having this lambda as the cardinal number. So with this fact one can see this is a full subcategory of the category set, and this is also isomorphism. Uh, so we claim this is skeleton, so that means this subcategory has to be isomorphism dense. So this is true, because if we pick any object, say A in this category, then there is some object B in this full subcategory which are isomorphic to A, because we say this subcategory has all cardinal numbers as object. as objects. Similarly, if we consider the category of vector spaces, so consider the category VEC of vector spaces. So consider the category VEC of all vector spaces. Uh, then the full subcategory uh, so which is determined by the powers say r to the m, where this m uh, runs through all cardinal numbers. It's a skeleton for back. So this is straightforward because again it's a full subcategory and isomorphism then a subcategory. Now we are going to prove a result uh, which says that every I mean the existence of the skeleton of a so this is the proposition. So the first item of this proposition is that every in category has a skeleton. So this is the existence of the skeleton. Second is that any two skeletons of a category are isomorphic. So the skeletons are unique up to isomorphism. So any two skeletons of a category are isomorphic. And third is that if we are given a category, say, I mean A, then the skeleton of A is equivalent to A. So any skeleton of a category, say A, is equivalent to A. So let us prove this. So consider the category A. Now let us define a relation on the object class of A. So define a relation. Let us denote this relation by this symbol here. So we are going to define a relation on the object class of A. So we define this as follows. So for any two objects, so for any A and A prime, I mean for any two objects A and A prime in the object class of A, we say, and A prime, A is related to A prime if and only if uh, A is isomorphic to A. A is isomorphic to A prime. So then one can see that this is an equivalence relation. So then one can note that this relation is an equivalence relation. Now, this being an equivalence relation implies that the object class of A has a partition into mutually disjoint equivalence classes. So hence, uh, the object class of A um, has a partition into disjoint equivalence classes. So now let us consider the set of all equivalence classes. So let um, the object class of A modulo. So we are identifying the elements which are isomorphic. So object class of A modulo this relation. So this denotes the set of all equivalence classes, all such equivalence classes. Now we can apply the axiom of choice to this set, and the axiom of choice allows us to pick one element from each equivalence class, and those classes, those elements will be no two such elements will be isomorphic, and that class will give us a subcategory. That set will be uh, so let us first write this down. So so apply action of choice to the set. So we have the set object class of A up to this relation, which are the set of all equivalence classes. So after applying this axiom, we get I mean we get the we get a skeleton of the category A, because so this is the object class of A. So by defining the this relation on this object, which says that A is related to A prime if and only if they are isomorphic. So this class gets partitioned into mutually disjoint equivalence classes. So this collection may be finite or infinite. So now what action of choice says, so that allows us to pick one object from each class. So this is the object A1, this is the object A2, and so on. So if we consider in this category, say let us call this S, where the object class is, so if we look at the object class of A, so if this is the, if this object class is in this set A1, A2, so on, AN and so on, then one can see that no two objects in this category are isomorphic. So this S turns out to be the skeleton of A. So this proves that every category has a skeleton. Now we we are going to prove that the skeletons are unique after isomorphism. So this is the second item. So let us suppose that the category B has two skeletons, say A and A prime. So let A and A prime be two skeletons of a category B. Then each A object, so if we pick some object in A, say A, is isomorphic to some object A prime. I mean, to some object in A prime, to some A prime object. Let us note this object by F of A. Now, what is this F? We'll shortly mention what is this F. Now, for each this A object, say A, what we choose? We choose a beam isomorphism. So we choose a B isomorphism. So this isomorphism goes like this. So it takes the object A to the object F of A. So then we have this functor. So then we have the functor F from the skeleton A to A prime, defined as, so it takes this pair, say A to A prime and this morphism F. So it takes this pair to, so object A goes to F of A. From F of A to A, we have this map here, F of A inverse, because F of A is an isomorphism, so it has an inverse. From A to A prime, we have the morphism H, and from A prime to F of A prime, we have the morphism uh, F sub A prime. So actually, this is given like this. So this functor takes the pair, I mean the morphism A to A, morphism A between the objects A and A prime, to the morphism, I mean to the morphism F of F sub A prime composite H composite F sub A inverse from object F of A to F of A prime. So this functor defined like this is an isomorphism. So by doing this, we show that any A object is isomorphic to prime object. So this means these two categories are uh, isomorphic. Hence, A and A prime are isomorphic. The third item is trivial. I mean, that follows trivially because uh, if S is a skeleton of a category A, then uh, the inclusion functor I from S to A is full, faithful, and isomorphism dense. Hence S is equivalent to A. So let S be a skeleton of a category, say A. So S being a skeleton, so then we have the inclusion functor. So then uh, the inclusion functor I from the category S to category A. So this is full because if we pick any object here, that is, um, I mean, if we pick some object to say B in A, so B is in the object class of A, that means B is in some equivalence class of, uh, so that means B is in some equivalence class. So B belongs to some equivalence class. Now, since S contains objects from all equivalence class, that means B is isomorphic to that object, and hence this I is uh, isomorphism dense as well as full. So it is, of course, faithful, and because it is inclusion, it is embedding. So I from S to A is full, faithful, and isomorphism dense. Hence, S is equivalent to A. So this proves the result.